So hello back everybody. So for continue, I will have a look to the question on Discord if there is some. So information we compare with AVX512. Okay. Normally, I will say MR equal native is better. MTune equal native is better, so you can pick the right architectures. But it depends on which one you start the test. If you test in the well optimized or the Laplacian, normally you should have a nice point. And if you get only 6%, oh yeah, maybe it's because you are looking to the pill loop and not to the full loop. So the pill is only 6%, but it's not vectorized because it's just generated by the compiler. So as I said, with I don't know this one. So this one is at the end, not at the beginning, but never mind. So this one is a pill tail. So you have 6% of peak computation performance, but it's not the main loop. And Macao will tell you normally it's supposed to be neglectable because it's supposed to be really small compared to what you want to do. Even if at some point in the VX512 you have some problem with that. So maybe you just have a look to the wrong one. Let this assembly analyzer assume instruction are scheduled such that each port that the utilization. Why does the latency appear around each port? Macao is not really good to predict what will be the real performances for the pipelining, but you will have normally nice idea of the speed up you can have. It will be not the right speed up because of the pipelining, but in terms of advice, normally it will be nice. Or maybe in the satellite sat, if you have some question, or there is no more question. Okay, so now we can do two things, but I think we can start with the first one. I'm pretty sure you want to develop, so we will develop. So if I summarize this, we have really bad performances here, but here we have a nice performance. And so this is in the 6 vectorization, so 64 example with the auto-vectorized Laplacian instruction. So I invite you to pick this one. So in the first exploration part of the project, and put this one inside. Typically, here you have a 6 vectorization, this one, and you will get the Laplacian light here implementation, and you can play with this one, pick this one, and create in 9 simulation here. You can add an extra directory to say, okay, I want to be able to produce some images with my Laplacian, because here it's only a performance test. So we have performances, we are happy, but we don't have a result, we don't have an images, we don't have HDF5. So here, if you put the example here, you will be able to have some real performances in a real test case. If you want, this is the exploration part. So really small pieces, small micro benchmarking, and this is the real production if you want. And you can try to use the backend. So basically, if you copy past one and you adapt and you put the Laplacian in it, normally should be quite okay. I think you can do that in maybe 20-30 minutes. So it's quite long, but the point is now you can you have information in the software. You get you know which one is the better one. Of course, it's the one missing. Then you can play with it and have a look. And again, yeah.
The people below it would be really easier to follow from below. They have the slides. So if you can upload them at some point, that would be great.
You mean right now or just after?
When you can, I mean, when you're in between two things.
Okay, because I'm practically done. So if you are an obtainer, it will be a bit difficult, but if you want to check, you can use the -- writable TMPFS, and then you can add some sources. No problem with that. Or you can get the sources with the targz or the sources inside the images, and you put them in a subdirectory and you edit them. It's also possible. Okay, so Adrien, what I propose you to do is to get the Laplacian implementation here in the 64 directory in the 6 vectorization. So the kind of the exploration of the project, and then you adapt it to be part of the 95, for example, Laplacian vectorization after the 94 here, to have this nice this kind of implementation. You have Grassroots initialization to create your matrix, Grassroots compute to do the computation, and Grassroots result to get the result back. And then we will be able to use the generic main I provide to you, which is here. So here you have the main we will use for the whole the 2 weeks, yeah, even for the GPU part. So you get the parameters, you get the even a progress bar if you want. You have the HDF5 stuff. We compute the images. We can take care about all the parameters, all the stuff, all the HDF5 in it. And we can also do much more, but we will not have time for this session. We will play with that later. And so the idea, if you get this this kind of stuff, so basically you can copy past one directory to create a 95 directory. Then don't forget to change this one. So here it's really pretty simple. You have the generic Grassroots compilation, and then you create your target. So for example, Laplacian O3 vectorized, and then you get the directory you want to use with your sources, your include you want to use inside your directory, and the option you want to pass. And normally you will be proud of you because you will have nice simulation, optimized simulation at the end of the session. Not totally at the end because I have the last thing to make you to do, and maybe in a quarter of an hour I will told you the last little thing you want to do, and you can mix them together, of course, if you want. You mean this one?
Yeah, I don't want to see what we will change it to the CMake to include the auto-vectorization. Can you come back to this, please?
You mean which one? This one?
Yeah, there is some change that we have to do in this. I did not flow properly.
This one is just to show you the dynamic probably sorry with this code, just to show you the optimization options here. But normally we get the same in this one here. So basically you can copy paste this one. Okay. If you get your 95 Laplacian, for example, directory, then you copy paste this one, and then you say I want this is Laplacian, and this it will be also I don't know 95, for example, Laplacian, and this is maybe also Grassroots. No, this one, Laplacian vectorization, then you do this kind of stuff, or maybe you can remove this one also. If you have Laplacian.h in your 95 Laplacian directory, and the function will do everything for you. You can do it step by step without this function if you want, but the point was not to make you program in CMake, just to make you integrate well in an existing stuff. The main point is how to pick the Laplacian and put it inside the real backend to make sure that everything is working. Okay, so maybe we can finish this morning with something a bit more fun, because developing is not always fun. And you will be able to combine the two if you want. So just to prepare the afternoon, let's ask ourselves a question. Can we determine the size and the shape of an image to be sure that we have the best performances in cycle per element on your hardware? So I made a little script, so in Bash, because I know the Bash is an horrible language, but it makes me laugh, so I'm sorry. And the idea is you get the script from your build directory, you pass one program in the 9 simulation stuff, and you can tell it, okay, I want to test this number, these different numbers of number of rows and this different number of columns, and it will make you a nice metric like this, and you can explore which one are the best, are the worst for your particular hardware. And of course, you can combine it and you can say, okay, I have a Laplacian ready. I want to check the size of the best image I can have on my laptop for the Laplacian. If you want to run some tests. So that's an idea for the beginning, but of course you can refine it with your laptop, with your hardware, depending on the result. And you will get this kind of plots. And then you can iterate and figure out which one is the better one. So this is the result for my laptop. But so here, basically, you will have really much rows than columns, and here the opposite. A lot of columns, but less rows. So I let you the command if you want to play with it. And so if you don't have your Laplacian yet, it's not a problem. You can finish it later and play with it later with this command.
Do you have a version of the code that we were supposed to build now?
New version, what do you mean?
Like the edited version of 64?
You can use whatever program you want here. If there are programs from the simulation part, so with the nice integration with the
No, I meant the task that we had to do right until now.
You
like
mean the
edit
Laplacian?
the auto-vector Laplacian light. Yeah, do you have the edited version?
Yeah, I have the correction. I didn't push yet to not spoil you, but I have the correction if you want. Yeah.
Maybe, yeah, I think you said that, but I was not listening. Why do you have like this small error where the performances are better at the center of this plot? Like why 128?
Yeah, I didn't say why. In fact, yeah, it's a good question.
Ah, okay, so perfect.
I didn't say why, but yeah. Basically, normally here, if you take a look, 128 is something. 22, normally, it's a bit bigger than the L1 cache here, I think. Oh no, oh yeah, I have to show you that also. That's a good point. If I do HTML look as so, here's Please come on. Thank you. So this is the processor I have on my laptop. So you see that it's quite complicated. And we'll also talk about that this afternoon. So there is a concept of core for the computation and core for the energy, economy of energy. And you have a look here, you see that these are really common cores. So L1, L1Y and L1D and L2 common are only for one core, and only the L3 is common. But for the energy efficiently core, there is no hyperthreading. There is hyperthreading here, but not here. And the L2 cache is common. Depending on what's going on, normally I ask GWlog to bind my test here on one of these core. And here you see on data I have 48K. So a bit more than 32 as usual. You should have, I think, the same, of course, in your laptop too. And the point is how to fit data in bits to be more efficient. Of course, we will see that with the advanced blocking, it's a bit more complex than this. But that's the idea of the classic blocking. You put your data in the L1 cache, and then you are faster to do the computing. And then you remove it, and you put another block, and you do it again.
What is the number? 48K? Is this the number of the L1 data cache? I cannot see.
It's in fact for most of years now it was 32 mainly 32K in N1D and N1I also, and now for the new architecture it's more than 48K and sometimes a bit more also, depending on the start to increase a bit. And of course here you have so it's 1 megabyte L2 and 2 megabyte L2 and 25 megabyte L3. Sometimes you can have also much bigger cache depending on the CPU. So you always have to not to do every study like this, but to ask yourself, okay, what is the size of my L1, my L2, my L3? Yeah. Are they common or not? So you can adjust your computing.
Okay, so now we have 128 times 128. This is like 16K elements.
Yeah, it's fit in the
like
L2.
4 bytes each, or
4 bytes each. So it L2.
So it is the maximum that fits in the L1.
And also here you see that I have big steps between everyone. So I'm pretty sure that if I zoom here, I will get other information here. But a large survey of everything. So of course, once you get that, you can zoom in and have a look. Normally, there is a zoom in inside the lecture. I didn't put in the slide, but you can have the details and precisely how to get that.
But then this is 58K. So it doesn't really fit directly in the L1.
Not the L1, the L2 in this case.
Oh, the L2. Okay.
But maybe, yeah, it's because here I have a big steps. If I do some study here, normally I will fit in the L1 and it will be much better. So that's the first step of the survey. And then you refine, you say, okay, let's zoom in this part because in this part we have the interesting stuff. And then you do another survey with the cells here, and you find the really best one. This is the first step. It's a really large first step corresponding to this command. And after that, you have to play with it or say okay, my better results are here, so I will take these four values, and I will increase the number of iterations here to see what's going on, which are the best ones. We will have to play with that. Here, for example, you have the same performances, but of course, you fit in the L2, whatever the size you have, you fit in the L2. So, but if you refine, then you will have some some asymmetry, and then you will have symmetry again in the end one. But it was quite complex to plot, so I did only this one. Okay, so if there is no more question, maybe we can go to lunch. We start the break, so we'll go back at 2 p.m. for the next step of this story. So with blocking and advanced blocking, I will do the presentation with Sébastien. And after that, we will have Adrien for the profiling lecture. So thanks everyone for being here during this lecture. Hope you learned some stuff. Hope it goes well also. And see you in a bit less than 2 hours.